Right. So the topic is part 2 in the series. There'll be a total of 3 on chemical bonding. And in part 2, we're going to take a look at the properties of ionic bonding using the methods of Lewis dot structure. Let's begin by taking a look at lithium and fluoride. Lithium has 1 valence electrons, so we're going to give it 1 dot. Fluorine has 7. And what we're going to do is bring the two together. And when we do that, what we notice is fluorine has 8 around it. Remember, a single bond accounts for 2 electrons. And lithium, because of the bond, has 2 electrons in the valence. Fluorine is satisfied, but lithium is not. So what we want to do is try to approach the problem by creating a double bond. Now lithium has 4 electrons, because there are 2 bonds, and fluorine remains with 8 electrons, so it's satisfied. But lithium is not. And because that atom is not satisfied, the valence shell is not full, it's considered unstable. So that molecule, that compound, won't form. Let's take another approach. Why don't we now try and make a triple bond? Once again, fluorine has 8 electrons around it, but fluorine only achieves 6 through a triple bond with fluorine. And again, 6 is not considered stable, so this compound will not form. And the reason why is there's not enough electrons to be shared with lithium, and the electronegativity difference is way too high. It's greater than 2, meaning that the electrons will be pulled very aggressively by fluorine, and lithium cannot hold on to it. So for both of those reasons, attempting to covalently bond lithium and fluorine is not going to work. So what other method could be used? Okay, so rather than covalently bonded, let's form ionic bond. What we're going to do here is we're going to allow lithium to give up completely its electron to fluorine. And it will do so because the electronegativity of fluorine, the pull fluorine has on the electron of lithium, is so great that it effectively strips it away. By doing so, lithium becomes a plus ion, fluorine becomes a minus ion. And fluorine now has 8 electrons on the outside. It's stable. Lithium, by losing the outside electron, assumes the electron configuration of helium, which is full, and now you have both sides stable. Now because we formed ions, lithium plus, fluorine minus, those 2 atoms now have an electrostatic attraction. Notice the electrons themselves are not involved in holding it together. It's simply the fact that the overall atom itself has these ionic charges, and an attraction gets created. If we were to take a look at lithium fluoride in a dish, which is shown there, it exists as a solid powder. It also we might refer to as it's a crystalline structure. So how does that work? Well, let's take a look right now at it. A crystal is made up of millions of ions. It's one ginormous ionic lattice. Now what does that mean? Well, in this example, we're going to take a sodium atom. Notice it has 1 electron on the outside, and a chlorine atom, which has 7. We're going to donate it. We're going to form 2 ions, and those 2 ions are going to be attracted to each other. But we're doing this again and again and again. And when you do that, you have this regular arrangement of alternating pluses and minuses no matter what direction you go in. And this repetition goes on for millions and millions of ions until the whole structure is a crystal. So what we just saw was how a crystal would look if you could look at it at the level of atoms. And so a crystalline structure is simply millions of ions attracted to each other. Let me see if I can advance this. Here we go. Trying to advance. So, what happens is, if you were to draw this out we referred to this as a lattice structure of ions, and it's a regular pattern based upon the ionic attraction or ionic bonds. The arrangement of the cations and anions, they attempt to maximize the positive attractions between the ions and try to make sure that the same ions, plus plus or minus minus, that repulsion is minimized. And this again is a drawing of this lattice structure, and this again is your ionic bonding. If you looked at it again in a large scale, look at the regular arrangements of the two different kinds of ions. That's a crystal. That's an ionic lattice. Now let's take a look at ionic bond again. Take a look here. Notice that nickel is going to give one of its electrons in the outside to the fluorine, and that creates an electrostatic attraction. Ions are being held together. But notice there is another electron to be donated, and that becomes a +2, and you now have an attraction of nickel fluoride. Now, when you in fact build the lattice, you will notice that in the next line, the pluses and minus alternate. And that again is a look at the repeating patterns of the cation anion. Now, one of the properties that all ionic solids have is their melting point tends to be very, very high. And the reason why is because the ions are surrounded by oppositely charged ions. There's lots of them. And so the overall attraction, the sum of all these attractions, is very, very strong. Now, when you heat these, the vibration does start to strain the attractions in the lattice work between them. However, what happens is, in order to weaken the bonds, you have to have a greater greater temperature to weaken the bonds, because the attraction is so strong. Now, one other property that ionic compounds have besides a high melting point is they tend to be very, very brittle. What that means is that if you hit them, they tend to shatter. Now, why is that? Well, we're looking at the nickel fluoride, and we're going to hit the lattice, or hit the crystal, right there at the nickel point. That moves that whole block and offsets it from the layer above it. And so now what you have is you have pluses right next to pluses, like the nickel, and minuses next to the minuses, and you now have created this repulsion. And therefore the crystal flies apart, and that's why the crystals are so brittle. Now, there's a lot of uses for different kinds of crystals. One of the most common one, of course, is going to be sodium chloride. That's table salt. This is just giving you an idea of the kinds of uses there are to salts. One of them, at the very top, 50% of it, is used in the process of making hydrogen gas, making sodium hydroxide. So chemical processes to make substances use sodium chloride a lot. But as you can tell, meat packaging is used, paper pulp. You have ideas that we use salt on the roads during the winter, because the melting salt gives off heat, and it causes the ice on the roads to melt. And so there are a number of very important uses for this simple crystal of sodium chloride. Now, where do we get the sodium chloride in such large amounts? Well, there are salt deposits, which we actually do use mining techniques for, but also it's used through evaporation. In the case of evaporation, very, very large areas allows the ocean to move in and flood an area. They then seal off the ocean so no more water can come in, and they allow the sunlight to evaporate it away over the span of a few months. Once the evaporation has taken place, the salt has been precipitated out, and what happens then is you could then harvest and get it that way. Located up in San Francisco, there is a very large evaporation method of obtaining salt that exists there. So there you go, ionic bonding and the formation of crystals.